Mr. Dean here. We're talking about the fundamental theorem of algebra today. And it has a big name, fundamental theorem of algebra, and it doesn't disappoint. It's big. What it states is that any polynomial of degree n has n roots, but we might need to use complex numbers to find them. In other words, all polynomials, every one we've ever studied, have at least one zero in the complex number system, meaning that now we know about imaginary numbers, all polynomials can be solved and they can be factored. For example, we know that even crazy long polynomials like this one in red is definitely solvable. Problem is, we just might not know how to solve it. We can thank Carl Friedrich Gauss, fundamental theorem of algebra. He proved it back in the 1800s, early 1800s. He proved that linear factors and irreducible quadratic polynomials are the atoms or the building blocks of all polynomials. All right. What it doesn't tell us how to do any of these factoring. Of course, we got the quadratic formula, and that can solve all our quadratic problems. And there is a cubic formula, but it's a really long process. It's not really known in general how to factor any kind of polynomial. Techniques for special kinds are known, and it's even worse than that. The French mathematician Évariste Galois, he died in a gun battle over a woman when he was only, if you look at the dates, he was only 21 years old, one of the best mathematicians of the last couple hundred years, both these guys. He proved that there will never be a general formula to solve polynomials of degree 5 and higher. So there's no way to do them with a formula. Let's get right to see how this affects us. Let's say we want to solve x squared plus 1 equals 0. It's a polynomial. According to the fundamental theorem, they can be solved. Here goes. We just subtract 1 on both sides, right? And now without complex numbers, imaginary numbers, we wouldn't be able to, take the square root of both sides here in a moment, we wouldn't be able to say that x is equal to plus and minus the square root of negative 1. X is equal to positive and negative I. If we look at the graph of the function y equals x squared plus 1, we can see that, of course, it doesn't cross the x-axis at all. What it does do is turn. There is a turn in the graph, and that will be significant later. But our solution is that x is equal to positive and negative I. Now let's talk about complex numbers for just a minute. You might remember it has a real part and an imaginary part. So all these numbers, that's a complex number. Even the number 9 is a complex number. All of these numbers are complex, all right? And when we talk about them, we say complex. Sometimes we're talking about solely imaginary numbers. Sometimes we're talking about a number that has a real and an imaginary part. It gets a little shady with it all. But usually when I say complex numbers, I'm talking about a number that has an imaginary part and a real part. It's complicated. Here goes. How complex numbers affect a graph. All right. Real zeros cross or touch the x-axis. We kind of know that, right? So you got a formula like a function like x squared minus 1. It's the x squared graph, but of course it comes down 1, so its vertex is down at y equals negative 1. Over on the right-hand side, we do not have real zeros. We have complex zeros. They do not cross the x-axis. All right? Remember the idea that an n-degree polynomial might have as many as n real zeros? Well, now we know. It's the real zeros plus the imaginary zeros that add up to exactly n. So a fifth-degree polynomial has 5 complex zeros. We just don't know how many of them are real and how many of them are imaginary. Let's take a look at some graphs. Of course, that's real. That has one real root, right? It's a straight line. It's a linear equation. Here's a quadratic. 2 reals, okay? 2 real roots. One there, one there. Here's a third degree. We're going to have to write it down, but 3 real roots. I see roots here. Must be 4 real roots. Now over here we have two graphs. This one might be like x squared plus 3, and who knows what this is, negative x squared maybe, minus 3. No real roots to them, no solutions. All right, now here's a combination now, right here in the middle. It has one real zero, but you know it has the shape of a third degree polynomial. It has one real zero. So where are the other zeros? Where are the other two? Well, they are imaginary. Where they we talk about where they are, is it causes this wiggle. See a little wiggle in the graph? That's caused by two imaginary zeros. And imaginary zeros always come in pairs. Really important idea. Here, the green graph here. We got four imaginary zeros, two pairs. There's two wiggles, and we certainly don't have any real zeros down the bottom on the x-axis. So let's think about how to sketch a fourth degree polynomial. It has one real zero at 3. All right, so it really goes through there. And it has a negative leading coefficient. So I'll use the idea of a negative leading coefficient in fourth degree. That end behavior is both down. All right, I only have one real zero at 3. So my graph, qualitative look at it, could look like this. But it's a fourth degree polynomial. I have one real zero at 3. Well, that one has to have a multiplicity of 2. Or it could have a multiplicity of 4. 4, we don't know. It's hard to say. All right? If it has a multiplicity of 4, then my graph looks just the way I kind of drew it. If it has a multiplicity of 2, where are the other two zeros? Well, the other two zeros might be a pair of imaginaries. Pair of imaginaries. And again, when I say imaginaries, I'm really talking about complex roots. And that pair of imaginaries would cause a wiggle somewhere in the graph. We just don't know where. All right, we don't know whether it's there, or perhaps that wiggle, this goes down straight, and perhaps the wiggle is on this side. We don't know anything really much about the wiggles, but we got that so far. All right, so either any of those three graphs would be fine. We've accomplished what we set out to do. Now let's get a little more official here. We got a fifth degree, has two real zeros at -5 and 4, so I'm going to claim those. All right, and positive leading coefficient, positive, and fifth degree. Two zeros there. I don't know if any of them double, but let's take a look, because we got one pair of complex. I know that the reals plus the complex has to equal, add them all up, and they're going to equal the degree, the n number. All right, the degree. Whoops, didn't spell that very well. So the real and the complex. So there's two reals. There's a pair of complex. That only adds up to 4. Where's the other 0? Well, you cannot have an odd amount of complex numbers. You can only have pairs. So that has to stay 2. It can't go up to 4, because then 2 plus 4 would be 6. So the extra 1 must be that one of these is doubled. One of these counts twice. One of these might come, say, from a factor of x minus 4 squared. We don't know which one. There's not enough information to tell us which one is doubled, so we'll just go with it. We'll say the 4 is doubled. So the 4 is going to have a multiplicity of 2. So really, instead of there really being 2, there's 3 roots counted in. This one's counted twice. This one's counted once. So the graph will go through at -5, but will bounce at 4, because a multiplicity, even multiplicities, always bounce. All right, lots to think about. Positive and fifth degree. The positive fifth degree, that end behavior looks like this, right? End behavior looks like that. So I'm going to come up through here. I'm going to bounce, and I need to remember somewhere I have to show this complex numbers. So I will put a wiggle somewhere in my graph. I don't know where it is. That wiggle can be here. You could have added a wiggle in here somehow. You could have added a wiggle kind of in that direction. As long as it's got a wiggle somewhere, the wiggles will be happy. Moving on. Now, let's really fully factor, including complex factors, including everything. Let's factor this whole entire thing. The fundamental theorem of algebra says everything can be factored, just takes some work. So let's go. I got x cubed minus 10x squared plus 33x minus 34. I'm going to set it equal to 0. The rational zero test tells me that these are all the possible rational zeros. So what I'm going to do is I'm going to plug each one of these back in and see if I get 0. All right? So believe me when I say I plugged in 1, I plugged in -1, didn't get very far. I plugged in 2, and I got 8 minus 40 plus 66 minus 34. It works because it got 0. So 2 was a factor, or a 0 really, that worked out, okay? So I know that x minus 2 is a factor. So I'm starting to factor it. What I'm going to do next is I'm going to divide by x minus 2. I'm going to use synthetic division, all right? I took the 2 out here. I synthetically divided. I knew I was going to get 0 as a remainder. I knew that already. These should definitely match up. But what's important is what's left over. 1 minus 8 and 17. All right? That means 1x squared minus 8x plus 17. All right? I will continue downwards. I know that, don't forget, I already have this factor, and now I know this is a factor. We've broken it up at least into 2 factors. Can I continue with this? Well, I tried to factor that normally. I didn't get anywhere. All right? So it's time for the quadratic formula. The quadratic formula revealed to me that my factors, my other zeros were 4 plus and minus I. This all comes from the quadratic formula over here. I was just simplifying and simplifying. All right. I got 4 plus and minus I. Those are the zeros that came from that quadratic. So now time to piece it all together. The zeros are 2, don't forget, because that came originally from the one I found, x minus 2, and 4 plus I, 4 minus I. All right. So I broke it all down. So I put it together as my factors. X minus 2. I have one real factor. And then I have x minus 4 plus I, x minus 4 minus I. Those non-real zeros look like that little wiggle. And of course, we go through 2. All right. One more joke for you about imaginary numbers. Thanks for hanging in there. This is Mr. Dean saying, keep it real. We're out.